Hey folks, welcome to part two. So we're continuing to talk about the mole and counting and weighing matter. So we just learned about the mole being a counting unit similar to a dozen or a ream or a case. So it is a special unit though, and it's used pretty much exclusively in chemistry. And you'll see in a few slides where this number comes from, but it's also known as Avogadro's number. So Avogadro was the scientist who kind of uncovered this value and defined it. And so he gets the honor of Avogadro's number. And as I tried to point out, it's 6.02 times 10 to the 23 anythings. It doesn't matter what you're talking about. It's such a big number that context is usually chemistry, but it really means anything. If you have a mole, 1 mole of atoms would mean that you have 6.02 times 10 to the 23 atoms. 1 mole of molecules, the same, right? And so again, it's just like the concept of a dozen. If you have a dozen eggs, you have a dozen pencils, you have a dozen nails, it doesn't matter what you're talking about, it means you have 12. And a mole means you have 6.02 times 10 to the 23. That would be 6, 0, 2, and then 21 zeros. So very large number, which is kind of daunting sometimes, but the goal is actually to make our lives easier so that we can talk about things like a mole of salt instead of having to talk about how many molecules we have here or something like that. So where did this number come from, the 6.02 times 10 to the 23? It's actually defined as the number of carbon-12 atoms in exactly 12 grams of carbon-12. Okay, if that makes sense. Let's break that down. So if you look in the periodic table, right, you'll see carbon, and we talked about this as the atomic mass, right, 12.01, and carbon 12 is actually an isotope of carbon that has exactly 12 total protons and neutrons, and so it would be 12 atomic mass units per molecule. But the way we've defined the number of moles is it's also 12 grams per mole, right? So we could write 12 atomic mass units per atom, or as a ratio, kind of like we did when we found the molecular mass of water earlier, right? Or magnesium chloride, or glucose. Now that same number also means grams per mole. Okay, so this is actually really quite useful, right? This means that that number in the periodic table, that 12.01 for carbon, that's the mass of an average atom in AMU, or it's the mass of a mole of atoms in units of grams. So when we talk about molar mass, it's the mass of a mole, it's grams per mole, that's right there on the periodic table. Okay, I'll keep mentioning that again and again as we use it. So the two main benefits of Avogadro's number, or the mole, are one that, as I said, it does make communication easier. It really does. So rather than trying to say 9.63 times 10 to the 23 molecules of water to somebody, you can say 1.6 moles of water. And that's the same thing. It's scaling it down to reasonable numbers. And two, it's a conversion factor between the number of particles and moles. So here we've represented it like a unit plan where we have a number of particles and moles, and they're connected by an arrow, which gives us a conversion factor, which we now know we can write two different ways depending on the problem, right? Depending on which way we're going and what we're trying to solve. Okay, how about a couple examples? Okay, so how many atoms of helium would there be in 3.5 moles? This would be about approximately the amount of helium gas that would be in a typical size balloon at room temperature. So how many atoms of helium are there and 3.5 moles. It's a one-step conversion. So we haven't done these in a couple of chapters, but remember we always want to start with the measured quantity, which is given in the question as 3.5 moles. We're going to multiply by our conversion factor. In this case, we want into atoms. So I'll put that on top. Divided by 1 mole equals 2.1 times 10 to the 24 atoms. Now, when you're writing and calculating with scientific notation, if you have a TI, Texas Instrument, you're going to want to find the EE button. It might be above the 7, so like a shift, and then that button above the 7 says EE. So if I'm entering, say, 6.02 times 10 to the 23, I type in 6.02, and then E, and then 23. Okay, and now the calculator knows that this is one number. Okay, it keeps the exponent, the E is for exponent, right? Attached to 6.02. This is really important when you're dividing. So let's try dividing, actually. So we'll look at the second question here. A silver ring contains 1.1 times 10 to the 22 silver atoms. How many moles of silver are in this ring? Okay, so we're going to start with measured quantity, which is atoms. So then I'm going to multiply with a mole on top times 6.02 times 10 to the 23 atoms. And I'm left with moles. I'll write it up here. And this ring would have 0.018 moles of silver. Okay, so if you did not get that, let's make sure we're doing the scientific notation right. So what I often see as the common mistake is students do this. Something like that, right? So 1.1 times 10 to the 22 divided by 6.02 times 10 to the 23. But if you do this, your calculator will multiply these numbers, then divide by 6.02, and then multiply by 10 to the 23. But that's not what you want to do. What you want is to divide by 6.02 times 10 to the 23. So you can use parentheses, or we can use the actual notation that your calculator has, which is the E button, again, like probably the shift button above a 7 if you have a TI, or on some others it might actually say 10 up to the X. But we would write it or type it into our calculator like this. 1.1 E22 divide by 6.02 E23. Right? Remember I said before, now the E23 is attached to the 6.02, and the calculator knows that you're dividing by this whole number, right? And so you'll get the correct answer calculation forward there. Okay, let's do one more example. 1 teaspoon of NaCl, also known as sodium chloride or table salt, contains 5.15 times 10 to the 22 formula units of sodium chloride. Now this is an ion, so we talk about formula units. 3 parts to this question. How many moles of sodium chloride are there in 1 teaspoon of sodium chloride? So go ahead and pause it and answer for yourself. Okay, so we're going to set this up just like the last question we did, where we start with formula units and convert to moles with the mole on top, right? So again, a mole is anything. So in formula units is the unit here that we're canceling out. And again, make sure you're entering this into your calculator correctly, and you should get 0.0855 moles of NaCl. Now the next question is how many moles of sodium ions does this correspond to? All right, so we know how much sodium chloride we have. How many sodium ions? Okay, so this is actually introducing a new idea, which is sodium chloride. Well, it's not new, but we're going to think of it in a new way. Each compound of sodium chloride, NaCl, has one sodium, right? And so you can think of this as another, hey, conversion factor. Everything's conversion factors to us. So I have a given number of sodium chloride, and for every 1 mole of sodium chloride, I have 1 mole of sodium plus, right? And so that's a conversion factor that cancels out sodium chloride and gives me Na plus. It's the same number, of course, as before. The third question is how many chloride ions does this correspond to? And maybe now you see the same step. Number of moles of sodium chloride and convert that into moles of chloride with a 1-to-1 ratio. And so we get 0.0855 moles of sodium of chloride, right? Okay, again, we'll pause and we'll come back for the next part here in lecture 5.1.